Nilesh?
Yeah, he's around. He's connecting his microphone.
Okay.
Hello.
Yeah.
Hi, Dr. Adya. Am I audible now?
Yes, you are audible.
Okay.
So, so the next talk will be given by Mr. Kumar Nilesh. So he did his integrated MS from ISR Kolkata, and for master thesis he finished it from ISI Kolkata, and his area of research is quantum blockchain and multi-party quantum key distribution. So go ahead, Nilesh. You can see your screen.
Okay. Yeah. Okay. Thank you, Dr. Adya. Let me share it. Okay. Please let me know if it is visible.
Yes, it is visible.
Okay. All right. So in this short presentation, I will describe architecture of a blockchain and how we can integrate quantum to make it secure against any adversary. So the purpose behind is that a classical blockchain relies on asymmetrical cryptography, and with the discovery of source algorithm, it was apparent that hello.
Nilesh, you have some background noise, please.
I thought it was not from me. I guess someone else is speaking.
1 second. Yeah. Okay. Okay. Go ahead.
Okay. Okay. Feel free to interrupt if there is some disturbance. Okay, so I was telling that with the discovery of source algorithm, it was apparent that a sufficiently large or powerful quantum computer could break the mathematical difficulty that we use in asymmetrical cryptography. Therefore, we either require a post-quantum upgrade to the existing architecture of the quantum of blockchain, basically the classical blockchain, or we need to create an inherently quantum blockchain. Okay. So, all right. Now the initial concept of this DLT, it can be traced back to Byzantine general problem before the blockchain or Bitcoin were introduced. Now the notion of the blockchain that we know today, that is a cryptographically linked, decentralized, and distributed database that forms a chain using time-stamped electronic data. It was first introduced by this two authors, Stornetta and Bayes. And the accountability and transparency of transactions is basically the key feature of a blockchain, which makes them appealing for a wide range of applications, such as we see in healthcare industry, government and organizations, finance, etc. So the initial components of any blockchain, whether it is classical or quantum, are like nodes. The first one is nodes, which is a form of an electronic device that keeps the network running by maintaining the local copies of a blockchain. The second one is blocks, of course, each of which has a cryptographic hash of itself and the previous block, as well as the timestamp and the transaction data. So the timestamp basically establishes that the transaction data existed at the time of block creation or publication. And the third one is miners, who create new blocks on the chain through the process that is known as mining. Okay, so the all right, so the blockchain is basically a ledger which contains transaction data. A block also has its own hash and the hash of the previous block in the chain. Whenever new block is created, its hash is calculated and stored in the block. If there is any change in the block, the hash will change too. So the block will be different than it was previous. Now the as I mentioned that every block contain the hash of the previous block and stored in the block hash that creates a chain that is linked together. Here, for example, we have a chain of 3 blocks. As you can see that each block contains its own hash and the hash of the previous block that is written in the top. So the block number 3 points to the block linear chain. And even a slightest change in the block's data will change its hash and the hash of all the block that follows, which alerts the network to that there is attempted change. This will keep the blockchain secure. Okay, further, it is a distributed ledger that is records in a shared form, ensuring that no single organization or any entity controls the entire system. So eliminating the use of any third party. Now, even though each node has its own copy of blockchain, they are transparent that whatever action that is performed on this distributed ledger can be easily viewed and verified. So in this network, everyone is allowed to join, and if you join the network, you will get a full copy of the blockchain. So let's see when any user creates a new transaction and how new blocks are added in any blockchain. So this new block is sent to all the users in the network. Then each user in the network need to verify that the block that it hasn't that is valid block and it has not been altered. So after a complete checking, then each node in the network will add that block at the end of their blockchain. Now all these nodes in the network then create a consensus. So they agree on what blocks they will add, what blocks are valid and what blocks are not. So the nodes will reject any block which does not satisfy this consensus. Okay, so where does quantum computer comes into the picture? As I already mentioned, a blockchain relies on 2 asymmetrical cryptography. Basically, the cryptographic hash function and a digital signature. Security based on this mathematical complexity is not unique to blockchain. Even most of the current cryptography, like Subhas was mentioning, is based on certain kind of mathematical encryption that are difficult to solve using current computational capabilities. And therefore, one of the most intriguing applications of quantum computers is breaking that mathematical difficulty that forms the base of currently used cryptography, whether it is AES or this SHA-256. So basically, quantum computers can speed up the mining process that can crack the SHA-256 hashing algorithm. So which will eventually lead to 51% attack. You might have heard of the 51% attack in blockchain. So further, quantum computer could also completely destroy the blockchain or Bitcoin's classical signature. So this seems to make a blockchain completely pointless and useless in post-quantum world. Now, the threats that I mentioned, that these threats actually inspired many recent studies in the conceptual design of quantum blockchain. Here, the data is encoded in quantum states, which is then converted into a quantum block. Okay, I hope I'm audible. I'm not disconnected.
Yes, you are audible.
Okay, thank you, Devi. So here are a few such approaches. Basically, Jaganforce in 2016, he introduced a quantum Bitcoin scheme for transaction. His scheme, however, was ineffective. After that, we have Rajan, who introduced blockchain using entanglement in time. The problem was that it lacked many details and security analysis. Further, implementing his protocol in large scale is difficult. You can store only up to 2 bits or 4 bits of information in that block. And more recently, a quantum blockchain based on weighted hypergraph was proposed. Although the concept was interesting, but the consensus was incomplete, and there was no way to recover back the encoded information. So as far as we can tell, the research and development of quantum blockchain is still in its early stage. So there are numerous issues that need to be addressed. So in this presentation, my main focus will be the quantum blockchain that is based on dimensional lifting generalized quantum grams with procedure. So here the construction of each block in the network is done by applying a non-democratic orthogonalization process to a multi-qubit state factor. This lifting requires fewer quantum capabilities, thus making it practically realizable in a small-scale quantum network. And the original Gram-Schmidt orthogonalization procedure that constructs this orthonormal basis, basically W1 to Wn from an order set of vectors V1 to Vn in any Hilbert space H is very well known, right? We can achieve this by defining W1 like this as V1 over norm of V1, and then we define Wk plus 1 inductively like this. So in our paper, we use different kind of generalization given by Havlicek and Svozil. This is a generalization that employs dimensional lifting. In this, the constant of linear independence on the initial states that was there in the original one is relaxed, and thus it extends the dimension of the original Hilbert space. I mean, say that because this constant of linear independence is relaxed, the range of state which can be orthogonalized using this method is bigger than the range that was possible using the original one. So the end result after this process is orthogonal, and projecting along the newly added dimension will give the initial state. We will get back the V1s from W1. The main point is it is easy to notice that even any rectangular matrix M can be extended to a non-zero scalar multiple of this orthogonal block matrix given by N. So the Wj representing the columns of N are not only mutually orthogonal but also have equal norms. So the advantage of this technique is also that we have a surjective partial isometry P. For this case, it will be just a projection map. So when it acts on the columns of N, it will give the original vector that we started with, that is Vj. So this was the main theorem that we used in our protocol. Now, taking into account of the overall structure of our protocol that I will describe. So the proposed blockchain is a public and permissionless blockchain, and it satisfies the following properties: that it has a decentralized architecture, it has a quantum network with distributed ledger in which every node possesses quantum capabilities like quantum storage and quantum state preparation, and these two are the only thing that any node requires, that is quantum storage and state preparation. And they also have a shared common quantum database. We know that the blockchain has a wide range of application, but for the sake of illustration, we consider the blockchain that manages digital currency called QCoin, something like Bitcoin. And we don't have to presume that every single node in our network is basically trustworthy, that we can trust that it will behave in a particular way. But as long as in our vote-based consensus, if the system will function properly as long as certain proportion of the nodes are trustworthy. So here I will try to describe the protocol in a pedagogical way so that all of you can follow. It's not possible to cover everything in detail, but I will try to give you a rough picture by going step by step. So each round of the protocol has these 4 phases. The first one is transaction phase, then the verification phase, then consensus, and then block linking phase. Okay, so the step 1 contains the creation of transaction. So this now consider a node, say Alice. She wishes to send Q coin to another node. Let's consider it to be Bob. So because it is Alice who wants to transfer her Q coin, she will initiate the transaction. We denoted it by TX and sign it with her digital signature. Okay, then once she has signed it, she will encode the transaction TX containing her digital signature, Bob's address, amount to be transferred, and all the sources of this fund. So this encoded state is then denoted by VI. Once this is once VI is created, then she will broadcast it to every node in the network. And for the transaction verification, once someone receives that, yeah, this transaction is performed, then for the transaction verification, they need to check few things. So we consider a transaction to be valid if and only the following holds, the following 4 condition holds. The transaction TX is properly signed by its sender, Alice. Second thing is the sender of the transaction TX is one of the receiver of the source of the transaction T. And third thing is the certification and signature of the both the sender and receiver is valid. And the last thing is none of its source has been redeemed before. So if these 4 conditions are satisfied, then we will consider the transaction to be valid. And subsequently, the unconfirmed transaction still it is valid, but it is unconfirmed because it is not confirmed by every node in the network. So these unconfirmed transactions will form the log and are aggregated together to form a block that we will call, say, preliminary block, because it is yet to be confirmed. Now, to confirm this block, we follow the consensus mechanism. Through the consensus mechanism, every node reach a shared conclusion regarding the transaction included in the preliminary block, the PI tilde. So the consensus algorithm employed in blockchain technology are basically divided in 2 basic types. I'm sure you might have heard of it. The first one is the proof-based consensus algorithm, which is typically seen permissionless blockchain, such as proof of work, that we all hear in the case of Bitcoin. And the second one is vote-based consensus algorithm, which are most commonly used in this permission blockchain. Now, each round of consensus consists of these 3 phases: the proposing phase, the voting phase, and the decision phase. However, I will not go through each of the steps because this was not part of our paper. But it's important that through consensus, we achieve a common agreement that, yeah, the block is a valid block. So how do we create the final block using the orthogonalization method that I described earlier? So the final block that are created using this generalized quantum Gram-Schmidt orthogonalization, it's a big word, because each block are added one by one in order of their timestamp. Let's say there is a party called Charlie who has already up to wi minus 1 tilde in his memory. These denotes actually the valid blocks. In order to add the ith block, the ith block wi in its blockchain, he uses this orthogonalization method on the preliminary block PI that was generated in the previous step. As we have already seen in the first theorem that I described, that additional dimensions were added in this process. Let's say that is denoted by M. There is no restriction on the value of M. However, it will provide the bound of maximum size of the blockchain that we'll see later. So the blockchain that is created so far is okay. Let me continue. Okay, sorry, I was getting a call. Yeah. Now is it fine? So up to this part, I was fine, or I have to go back? Because I was getting a call, that's why I got disconnected. Is it fine now? Okay. Okay, then let me continue. So I was telling that up to this part, the block is unencrypted. That we have not applied any encryption scheme. So the encryption scheme is applied to the part of the additional dimension that I was talking about. Recall that this is called orthogonalization with that implies dimensional lifting. So the block is divided into two parts, the disclosed part and the second part is encrypted part. The encrypted part is the part where in which additional dimensions were added. Now the disclosed part will remain in the computational basis, but the encrypted part will be now encoded in psi theta. And the theta is basically a rotation operator. So it is selected by each user based on their preference, so that any other user is not aware of this rotation operator. And because no other member has access to this encrypted information of the block, so all other users, so for all other users, it is an unknown state and thus protected by no cloning theorem. And as for the practicality of our protocol, we have assumed that in our model, whenever Alice broadcasts her transaction, we say that not everyone in the network hears the transaction, like the classical or Bitcoin case. So it might happen that one peer hears one transaction before the next transaction, while other hears the transaction in a different order. So this is a different case of forking than a double spending case that you might have heard in case of digital currency. But luckily, for our proposed scheme, theorem 5.1 from our paper, it resolves this issue that even if other node here the transactions in a different order, it does not matter. Within a local unitary operation, they can get back to the original or the chain that is common with every other user. So the quantum blockchain scheme that is presented here is secured by non-democratic nature, or also known as sequential nature of the generalized Gram-Schmidt orthogonalization and quantum no cloning theorem. This theorem basically provides the security argument. This guarantee that the security of blockchain, in the sense that no transaction can be modified without changing the final state of the blockchain. So if someone tries to alter any transaction from the ith block of, let's say, Charlie, then it immediately invalidates all the successive blocks as they were orthogonalized with respect to the ordered state, right? Containing the encoding of ith block. So if ith block, initial ith block transaction in the ith block is changed, the orthogonalized state of the ith block will also change, and it will also change all the blocks that are orthogonalized after the ith block. It is somewhat like the standard classical blockchain protocol, but in comparison to the standard blockchain protocol, where only hash of the previous block is encoded in the next block by the linearity of chain. In this case, it is more robust than this just linearity of the chain. In some sense, information of all the prior blocks that have appeared before the particular ith block is encoded in that ith block. So this is because altering any state immediately invalidates all the blocks that come after it, not in a linear way, but it immediately affects all the blocks that comes after it. And we also have another theorem called the correctness theorem. So basically, it says that given a particular state of transaction, the final blocks that are obtained using our method is unique. Okay, so this summarizes the algorithm of the blockchain presented in our paper. I have already gone through most of it step by step. Let's just skip this part. Okay, so we can also present a quantum token that is based on the architecture of the proposed blockchain. So basically in the quantum token, the classical bits denoted by CI and the quantum bits, let's say QI, should be in one-to-one correspondence. Like for every qubits, a sequence of qubits, there is a particular classical bits in a one-to-one correspondence. And as in the case of the majority of quantum money scheme, the main idea is based on the no cloning theorem, which states that unknown quantum state cannot be copied. So to create a quantum token, basically we follow the same architecture as our own the quantum blockchain. No, the main difference is quantum token is a physical quantity, so we don't have to worry about the forking scenario or double spending scenario. So finally, these are the list of some common applications of blockchain that we are seeing today. I don't have to describe it because everyone are aware of the usability of blockchain. And these are some common references that has been proposed for the conceptual design of quantum blockchain. Again, these are just the conceptual design. We have not implemented any of these protocols in actual quantum computer. Okay, thank you.
Okay, thanks, Nilesh, for this nice talk. So we have enough time for the questions. So there is one question in the chat box from Devdat Sharma. So his question is, can we use concept of entanglement in time from blockchain formation? This is one of his question. And second question is, how this entanglement in time-based blockchain different from yours?
Okay, so as I described, Razan has already proposed this blockchain using entanglement in time, and it was in 2018, I guess. So basically, in entanglement of time, there's few advantages that I can say that that is present in our blockchain scheme than that is not present in Razan's one. Further, because entanglement is a very delicate thing, it requires a good quantum computer that with a lot of error correction scheme. In our blockchain, it does not require that much of quantum capabilities from the users. It just requires that you can create a quantum state and you can store the quantum state properly. So it is easier to implement our protocol. Further, we don't have any security proof for that one, the entanglement in time blockchain scheme. Because that's one point that I already mentioned in this in the presentation, that they were not able to provide a proper security proof of their protocol. But we have, as I mentioned in the security theorem, that we have provided a proper security proof for the blockchain that we have proposed. So you can say that this is provably secure than that one, the entanglement in time. And also the other point was that you cannot store a big amount of information using entanglement in time. They were using something like a state similar to this Bell states. So they can store up to 2 bits of information in each block. That was one restriction from their end.
Okay, I think they've got his answer. So thank you, Nilesh, once again.